Hello everyone, this is Mr. Underkoffler. Today we're going to look at the guided notes called Theoretical Probability of Simple Events. Alright, follow along with me here as I read this out loud. It says, in a probability experiment, the set of all possible outcomes is called the sample space. To find the sample space, you can make a list of each unique outcome. For the purpose of listing the sample space, repeated outcomes are only listed one time. Also, the sample space is not dependent upon actual results. So it's not dependent upon a relative frequency table or anything of that sort. All right, for example, and we're not going to do a lot of examples here on sample space. We're basically just going to do one here. It's a pretty simple idea. The spinner shown below is spun once. What is the sample space? Now remember, repeated outcomes are only listed once. So hit pause on the video, make your selection, and then hit play to see if you got it right. Okay, I hope you already did this problem on your own. Choice A is obviously wrong. There is no turtle or pet rock, which is pretty funny, on the spinner. So is it B or is it C? It's not D. There's definitely a lot more than fish. Ignore the fact that the pointer is pointing at fish. That does not matter. We are talking about the actual sample space, which is the possible outcomes. It's not going to be B, it's going to be C, and there's only for one reason. Repeated outcomes are only listed one time. So that is an important thing to know about when you are listing the sample space. You only list each repeated outcome only one time. Okay, let's move on from sample space. We will revisit sample space when we get to compound events, which is a future guided notes packet that we will do later on. Okay, let's talk about theoretical probability. Now, before we do, let's talk about uniform probability models are experiments, such as rolling a number cube or tossing a coin, in which all of the outcomes are equally likely. Well, theoretical probability is based on uniform probability, or what should happen in a probability experiment. Now, I want to underline the words should happen. Theoretical probability is not based on the same thing that a relative frequency is based on. It's not based on somebody's actual trials of doing an experiment over and over and over and over again and recording those results in a table. That would be relative frequency and experimental probability. Instead, theoretical probability takes into account the number of, for example, sides of a coin, there's only 2, or the number of sides of a number cube, there's only 6, or the number of spaces on a spinner, which could be different depending on what type of spinner you have. That's what theoretical probability takes into account. So the definition, the fraction, is really similar to relative frequency and experimental probability, except there are a couple things you should notice, and I've already highlighted them for you here. The numerator will be the number of ways an event should occur. So it's not based on what actually occurred from multiple trials of an event. Instead, it's just, well, how many ways should it occur? Like if I flip a coin, how many ways should I be able to get heads? Well, it'll be 1 out of 2. If I roll a number cube, how many ways should I be able to get a 4? Well, there's only 1 4 out of 6. So that's what theoretical probability is all about. The denominator will be the total number of possible outcomes. Not actual outcomes from multiple trials, but possible outcomes. Okay, let's do a couple simple examples together. A number cube is rolled once with sides 1, 2, 3, 4, 5, and 6. You can see 3 of those sides right here on this picture. What is the theoretical probability of rolling an even number? Well, here's what you got to think. We don't have a table of values. This is not relative frequency. We just have to think, I should be able to get an even number from rolling either a 2, a 4, or a 6. So how many ways is that? That is, boom, 3 ways. Go ahead and fill that in. So what's my fraction? What's the number of ways that the event should be able to occur? Well, that would be 3 possible ways of getting an even number. What is the total number of possible outcomes? Well, from a number cube, there's only 6 possible outcomes. You can see those listed right up here. So that would be out of 6. Now, this obviously reduces to 1/2. I hope you're writing all this down with me as I reveal this. As a decimal, you probably already know 1/2 is 0.5. If you didn't know that, you would have done 1 divided by 2 in your calculator and got 0.5, but I think everybody has this one memorized. And then as a percent, you move the decimal point 2 places to the right and gives you 50%. All right, that was a really simple example, but I want to get us started with making sure we understand what this is all about. Problem number 3, let's do this one together. A tile is randomly selected from the group below. What is the theoretical probability of selecting a number greater than 7 or a number less than 6? You're going to write the answer as a fraction in simplest form and as a percent. Now, pay attention to this reminder box. When you have the word or in any kind of relative frequency or probability problem, you will add the parts together. Okay, so what are we trying to get? We are trying to find the probability of selecting a number greater than 7 or a number less than 6. Okay, so which numbers were greater than 7? That would be the 8, the 9, and the 10. That's 3 numbers, but what about the numbers that are less than 6? That would be the 5, the 4, and the 3. 6 is not less than 6. 7 is not greater than 7. So we're looking at 3 numbers less than 6, 3 numbers greater than 7. So 3 plus 3 gives us 6 possible ways that we could get a number that's either greater than 7 or less than 6. And out of a total of 8 tiles. All right, let's reduce. This would give you 3 fourths. Now, you probably already know that that is 75%. So I don't really know if you have to show the decimal value if it's a super common percentage like 1/4 or 3/4 or 1/2. You probably have those memorized. Okay. Now, at the top of the next page, I put a little reminder section. I know back in math grade 6 and also maybe 5th grade, you were probably taught what prime numbers are and composite numbers, but maybe you forgot them. So at the top of the page, for your convenience, I'm reminding you what prime numbers are and what composite numbers are. And I've given you a couple examples of composite numbers and why they're composite numbers. And I've also given you a ton of prime numbers listed here. All right, use that information to help you with some of the problems coming up. So why don't you go ahead and try numbers 4 and 5 on your own. And then, you know what? You might want to try number 6 as well. It's a little wordy, but I think you'll be able to handle it on your own. So hit pause on the video, do 4 and 5 on your own. Feel free to use this top section to help you for one of these problems. And once you're done with 4, 5, and 6, hit play to see how you did. Okay, have you already done number 4, 5, and 6 on your own? Problem number 4, we're looking for the theoretical probability of spinning a multiple of 4. Multiples of 4 would be like counting by 4s. 4, 8, 12, 16, which is not on the spinner, 20, which is not on the spinner, and so on and so on and so on. So there are only 3 multiples of 4, and there's only a total of 6 spaces on this spinner. We don't add these numbers together, just like we didn't add the numbers together back here with the tiles. There was only 8 tiles, and that's where our denominator of 8 came from, where there's only 6 spaces on the spinner, so that's where the denominator of 6 came from. If you already realize that you therefore totally messed up 4 and 5, please feel free to hit pause and fix them up, and then hit play once you're ready to see how your new results match up with the right answers. Okay, so 3 6 reduces to 1/2. If you already knew it was 1/2 and didn't want to make a 3 6 at the beginning, that is fine with me. Hopefully you have memorized that 1/2 is 50%. And yes, these directions want us to write them as a fraction in simplest form and as a percent. Problem number 5, the theoretical probability of spinning a prime number. Now, I hope you use the section at the very top of the page. 1 is not a prime number. 0 and 1 are actually considered neither prime nor composite. And here's why. Prime numbers are supposed to have 2 factors, 1 and itself. Well, the number 1 has only 1 factor. So it's actually not good enough to even be prime. Now, it's definitely not composite either, but it's not good enough to be prime. Prime numbers have 2 factors, 1 and itself. Like the factors of 2 are 1 and 2. The factors of 3 are 1 and 3. The factors of 5 are 1 and 5. So that's how prime numbers work. Okay, so now that we know that, which numbers here were prime? Not 1, but 3 was prime. You can find it up here on the list. And 7 is prime. You can also find that up here on the list. So that was it. 4's composite, 8's composite, 12's composite. They have 3 or more factors. And 1 is not good enough even to be prime. It's neither prime or composite. So we are talking about 2 numbers that were prime out of 6 possible outcomes. That reduces to 1/3. 1 divided by 3 is 0.3 repeating. Move that 2 places to the right, 33.3 repeating percent. And yes, I mentioned this before on other lessons. You can have a repeating decimal as part of a percent. You should not round it. Make it 33.3 repeating percent. Okay. Problem number 6. We have the 50th anniversary. We got the kids who are now adults deciding on the flavors, but the mom's not with them. So what does mom like? What does mom not like? Well, it tells you right here that she likes pretty much everything except for lemon zest and coconut cream, which I kind of agree with the mom. I don't really like those flavors either. Not that you really care what Underkoffler thinks, but anyway. We are trying to find the probability that they will pick a cake that their mom actually likes. So she doesn't like lemon zest or coconut cream, but she likes everything else. So she's going to like vanilla, she's going to like rich chocolate, she's going to like red velvet, won't like lemon zest, she will like caramel, she will like the chocolate peanut butter. I hope this is not making you hungry. She will not like coconut cream, she will like the strawberry shortcake and the carrot cake. I very much like carrot cake. So what is this? 1, 2, 3, 4, 5, 6, 7. That is 7 different types of cake that she likes out of the 9 possible choices. I bet some of you just took the lemon zest and the coconut and counted that as 2 that she didn't like and subtracted that away from 9 to figure out that it was 7 that she would like. Totally wonderful logic if you thought that way. 7 divided by 9 is 0.7 repeating. Move the decimal point 2 places to the right, and you're going to get 77.7 repeating percent. And I forgot to put the repeating bar here, so let me go ahead and fix that right now. This is a repeating 7. Okay. Let's talk at the bottom of the page about theoretical probability and likelihood. Theoretical probabilities can correspond to the likelihoods that we talked about on the very first page of guided notes in this unit. We talked about impossible, unlikely, equally likely, likely, and certain. And I probably already told you back then that impossible was pretty much 0% chance, and certain was when there was a 100% chance. Well, if it's less than 50% but greater than 0%, we're going to call that unlikely for probabilities. And if it's greater than 50% but less than 100%, we're going to say that that was likely to occur. And then, as you would probably think, equally likely to occur as to not occur, we're talking about a 50% probability. Okay. With that in mind, turn the page. Problem 7 and 8, why don't you go ahead and try them right now on your own, read them, and use what we were just talking about at the bottom of the previous page to help you. So hit pause now, do 7 and 8, and hit play when you're ready to see how you did. Okay, have you already done numbers 7 and 8? If not, you better hit pause now. We have 8 gold marbles, 6 silver marbles, 2 bronze marbles. The best description for the likelihood of selecting a gold marble. There's 8 gold. Well, did you add this up? 8 and 6 was 14, and 2 was 16. 8 out of 16 is exactly 1/2, which is 50%. So that would be choice E, equally likely to select as it is to not select a gold marble. Problem number 8. A letter from the word nouveau is randomly selected. The best description for the likelihood of selecting a vowel is, well, let's count how many letters we have. 1, 2, 3, 4, 5, 6, 7 letters total. So an odd number. And we got 1, 2, 3, 4, 5 vowels. A very unique word, the word nouveau. Okay, so 5 of them out of 7. That's definitely more than half. So it's over 50%, but definitely not 100%. We are talking about being likely to occur. It is very likely that you would select a vowel if you're picking one at random, which is what this problem was talking about. Okay, the remainder of these guided notes on complements, I'm going to do that as a part 2. So I'm going to go ahead and finish up this video now. Thank you for watching. We'll see you next time.